Now let's get back to partial differentiation. Okay, so just remind you the definition of a derivative. Okay, and how did we get that in maths 1? Okay, so we have this point x here, and we have this point x plus delta x. Delta x should be very small, but to make it understand, when you zoomed it, okay, otherwise it should be very close together. Then we have a secant coming this curve, cutting this curve at this point. So what are we going to have here? This would be f of x, and this would be f of x plus delta x. Okay, the slope of this sequent, what slope? Slope is rise over run. So slope of this sequent would be f of x plus delta x minus f of x, which is the rise, and the run is x plus delta x minus x. They're going to get cancelled. You'll be left with delta x. What we want is, we want the slope x. Right? Now, if you make delta x smaller and smaller, this secant is going to tend towards this tangent. Okay, that would be limit of delta x tends to 0, and we'll just label this f prime of x. Okay, now derivative in 3D is something like this. There's just one additional now we don't have a function of one variable. Okay, should I just right, okay, let me just take it out. I just wanted to remind you what formula is. My function is to f of x and y. Okay, I'll draw the diagram as well. If we change x by very small amount but keep y constant, then the change, the functional value would be this. This would be the rise then. Okay, and we're taking partial derivative. So the run is in one direction. Increasing x, y remains as such. So you only have delta x. If you take a limit of this with delta x tends to 0, then you have the slope of this function when y doesn't change but x changes by a small amount. This would be partial derivative of the function with respect to x, the function which is of two variables x and y. Okay. Exactly something like this would be for y. So if we keep x constant and change y by a very small amount, the rise would be this, the run would be delta x. We're running towards increasing y, x is constant. If we apply limit delta y tends to 0 of this, we're going to have partial derivative with respect to y of a function which is a function of x and y. Okay, how, what's the geometry of this? I also hinted the geometry of this in yesterday's class, but till then we are not done planes. Till then we are not done planes of x is equal to a and y is equal to b. That was the piece we needed to know to understand this properly. Okay, what is this? This is kind of is leaning over. Okay, is that it's leaning over, it's hollowing between. What we have here, this point is 0 b 0. Okay, now it's not a plane like we have, but all across this it's like solid. The value of y is b. Okay, now if we move anywhere on this, what we have? We have change in x and change in z. That's what we need for partial derivative. If we take a point over here, let's say, just say this is b. Okay, b2 on the y-axis. This is b1 on the x-axis, and you have this point P over here and this line tangent to this curvature, okay, at P. F of x of a function, which is function of x and y, at b1 b2 is equal to the slope of this line at P. I've taken this point P, which is straight above. Okay, we don't know. Till here, we don't know what is the functional value of P. Only thing we know is what is the slope of the tangent line at P. So we take partial derivative slope, and this is the numerical value. It's not a function. You must understand. If we don't put these values here, then f of this is a function. The moment we put these values, it becomes one numerical value. Okay. Now, if we take another point Q, what should be the value of y at Q? It should be b2, because all across this plane the value of y is constant at b2. b1 prime. So the slope of this one is going to be f of x xy at b1 prime and b2. Does it make sense now? Should be clear now. Okay, so this is point P, this is point Q, this is B2, this is B1, this is B1 prime. Right, we can have something very similar for partial derivative with respect to y. Now you should know which way are we going to slice it. We're going to slice it at x now. Let's say this is A1, this point here. Let me write it bigger. This is A1. So all across this plane it's going to like this. It's going to cut x-axis at A1. If we take a point here, and this is A2, and straight above this we have our point P here now, straight above this. Slope of line this way, just touching this. Okay, so remember it's touching this, and this is just one line over this entire surface. So this line is touching this surface at just one point. I explained yesterday, we're not going to be concerned with the entire tangent plane here, concerned with these lines till now. What would that be? The slope of this line is f of y. This is partial differentiation. This function with y, we're keeping x fixed. Here, we're keeping x fixed at A1. This is the numerical value of the slope here.